On August 12, 2026, the moon will pass between the Earth and the Sun for a few minutes in a narrow band crossing Greenland, Iceland, northern Spain, and a sliver of Portugal. Day will become night, stars will appear, the temperature will drop, animals will behave as if evening has suddenly arrived, and anyone standing in that path will experience one of the rarest things a human being can witness with the naked eye. It's called totality, and it lasts, at most, 2 minutes and 18 seconds. What makes a total solar eclipse so striking is obvious. What makes it scientifically extraordinary is something almost no one thinks about when they're standing there with their mouth open. The sun's diameter is about 400 times larger than the moon's. It is also, almost exactly, 400 times farther away, which means that from the surface of Earth, they appear to be the same size. Not approximately, not roughly, the same size. Precisely enough that the moon can cover the sun's disk completely, edge to edge, leaving only the corona visible. This near-perfect apparent size match doesn't occur with any other planet-moon pairing in our solar system. It is, by any honest measure, a cosmic coincidence of spectacular proportions, and it won't last. I was looking into the geometry of the solar system when I found myself pulling on a thread I hadn't expected. The eclipse isn't just a visual event, it's a window. And not only into the sky, so I went deeper. The sun's diameter is roughly 1.4 million kilometers. The moon's diameter is about 3,500 kilometers. The ratio is approximately 400 to 1. The sun is also about 150 million kilometers from Earth. The moon is about 384,000 kilometers away. The ratio, again, is approximately 400 to 1. This alignment is what allows total solar eclipses to happen at all. If the moon were slightly smaller or slightly farther away, it would never fully cover the sun's disk, and we would only ever see partial eclipses. The exact match is what gives us totality, and the chance to see the corona against a completely darkened sky. No other planet-moon pairing in our solar system produces total eclipses with this same near-perfect apparent size match, where the moon covers the star's disk almost exactly edge to edge, leaving only the outer atmosphere visible. Is this meaningful? Almost certainly not, in any cosmic sense. The solar system contains enormous numbers of planet-moon combinations, and the laws of probability suggest that some of them will produce striking coincidences. Ours happens to be one of them. But almost certainly not meaningful is not the same as not striking. The precision of the ratio is genuinely unusual, and it has, more than once, turned out to be useful. Here's the strange part. On May 29, 1919, two teams of astronomers set out for opposite ends of the world. One traveled to Sobral, a small town in northern Brazil. The other, led by Arthur Eddington of Cambridge University, sailed to the island of Principe off the west coast of Africa. They were not there to watch an eclipse. They were there to use one. Einstein had published his general theory of relativity in 1915. The theory made a concrete, testable prediction that light, passing close to a massive object, would be bent by that object's gravity. Not slightly, by a specific amount, 1.75 arcseconds for light grazing the edge of the sun. This was almost twice the deflection that would be predicted by treating light as a particle subject to Newtonian gravity. The problem was that you couldn't normally see stars near the sun. The sun's glare made them invisible. A total solar eclipse was the only way. During totality, the sky darkened enough to photograph stars that would normally be washed out, close to the sun's edge. Eddington photographed the Hyades star cluster, which happened to sit near the sun on that date. He compared the positions of those stars during totality with photographs taken months earlier when the stars were visible at night. The positions had shifted by almost exactly the amount Einstein's theory predicted. The announcement was made in London on November 6, 1919. The next morning, newspapers across the world carried the story. Einstein, who had been largely unknown to the general public, became the most famous scientist on Earth, a status he never really lost. A 2-minute window of darkness, produced by a geometric coincidence, had confirmed the most revolutionary theory of gravity in 300 years. Now, set the physics aside for a moment. Arthur Eddington arrived on Principe in late April 1919. He had 6 weeks to prepare and a great deal to worry about. The island was in the Gulf of Guinea near the equator, and eclipse day, May 29th, fell at the height of the wet season. A single overcast sky would ruin everything. On the morning of the eclipse, it was raining. Eddington waited. The rain continued through the morning. He had traveled across the world with borrowed equipment from Oxford Observatory in the aftermath of a world war to photograph a 2-minute event. He had one chance. No second expedition was planned. Shortly before totality, the clouds began to thin. He photographed through breaks in the cloud cover. Most of the plates were useless, obscured by cloud, the stars invisible. But a few came through. 16 photographic plates were taken in total. The usable ones showed the star positions had shifted by 1.61 arcseconds, within the margin of error of Einstein's predicted 1.75. It was enough, not proof in any final sense. The error bars were wide, and more precise confirmations would come decades later through radio telescopes and satellite measurements. But it was evidence, real, photographic, measured evidence, from a team of British astronomers who had traveled to the edge of the world during wartime to test the theory of a German-born physicist. The New York Times headline read, "Lights all askew in the heavens." Eddington, by most accounts, was already certain before he finished developing the plates. He had understood Einstein's theory well enough to know what he was looking for. He found it. The moon drifts farther from Earth every year. Not quickly, about 3.8 centimeters annually, but the cumulative effect over geological time is significant. This drift is caused by tidal interaction. The moon's gravity raises tides in Earth's oceans, and those tidal bulges exert a gravitational pull on the moon, gradually transferring angular momentum outward. The moon moves slowly away from Earth. Earth's rotation slows slightly in return. Both effects are measurable. The numbers are precise enough to work backward. Roughly 1.4 billion years ago, a day on Earth lasted about 18 hours. The moon was significantly closer. Solar eclipses, when they occurred, would have looked different. The moon would have covered more than the sun's disk, leaving no corona visible. They are also precise enough to work forward. In approximately 600 million years, the moon will have drifted far enough that it can no longer fully cover the sun's disk. Total solar eclipses, the complete covering, the corona, the 2 minutes of darkness, will no longer be possible from Earth's surface. They will be replaced by annular eclipses. The moon will cover the center of the sun, but leave a ring of light visible around its edge. Visually striking, but different. The corona, the outer atmosphere of the sun, visible only during totality and scientifically invaluable, will be permanently obscured by that ring of light. The 400-to-400 ratio that makes total solar eclipses possible is a temporary feature of this moment in Earth's history. We happen to be alive in the window during which they occur. Dinosaurs did not see them this way. The descendants of whatever species lives here in a billion years will not see them this way. This is the window. August 12, 2026 is one of its dates. The August 12, 2026 eclipse will be the first total solar eclipse visible over mainland Europe since 1999. Anyone standing in the path of totality across Iceland or northern Spain will experience something that their grandparents may have never seen, and that their distant descendants may never see again. Not because eclipses will stop, but because the geometry that makes total eclipses possible is slowly, measurably ending. The moon will be gone from that position in the sky in a few 100 million years. The 400-to-400 ratio will no longer balance. What Eddington understood, standing on a cloudy island in 1919, is that the coincidence was useful. The eclipse was a tool. The darkness it created was a window through which, for exactly long enough, you could see something you couldn't see any other way. The same is still true. Look while you can.